Welcome to the solution for problem number 1 on the AP current electricity problem set. Let's start by reading the problem. A high voltage transmission line with a resistance of 0.310 ohms per kilometer carries a 1000 amp current. The line is at a potential of 700 kilovolts at the power station and carries the current to a city located 160 kilometers from the station. Now, as we go back through the question, we're going to underline the key piece of information provided and identify the variable for each. We have a high voltage transmission line with a resistance of 0.310 ohms per kilometer, and this is not the resistance, but the resistance per distance that we're given here. So we'll keep an eye on that. Carries a 1000 amp current. This is clearly the I value provided in the problem. The line is at a potential of 700 kilovolts. Okay, so this would be the original V value at the power station. There's the key on that. Okay, that's why it's the initial voltage. And carries the current to a city located 160 kilometers from the station. So there's the D value we mentioned up above. And that's how far away, how far the electricity gets carried. A, what is the power loss due to the resistance in the line? Okay, so they want the power loss for A, and what fraction of the transmitted power does this loss represent? Well, this would simply be the amount of power in the line at the end of the 160 kilometers, so at the city, divided by the initial power at the power station. So that would be the fraction of transmitted power this loss represents. All right, let's start with A. Power loss is different than change in power. To calculate a change in any quantity, we take the final minus the initial. But if we were talking about a loss, we would start out with, well, how much did we start with? That would be our initial power in this problem. And subtract from that, how much did we have when we were done? That would be the power loss. Notice that that's different than the change in power. Well, I think we have enough information to find the initial power. All we need is 2 electrical quantities given for us at the power station, and they told us that the initial voltage was 700 kilovolts and the initial current is 1000 amps. So we'll go to the version of the power equation that has those 2 electrical variables in it, P equals IV. We'll substitute in our 1000 amps and our 700, and we need to do kilo. Kilo is times 10 to the 3rd. And this would give us a power of 7 times 10 to the 8 watts. All right, so now our job, now we have the initial power, now we have to figure out the final power. That means we need 2 electrical variables for the final power. We already have one because the electrical characteristic that doesn't change in this problem, you can think of the wire, the long line carrying the electricity, as a long resistor, a long series circuit, one path for the current to flow. Well, electrical characteristic that remains constant for that is current. So we know that we still, when the electricity reaches the city, that it will still be 1000 amps of current. The issue is that we lose voltage. The voltage won't be the same, and at some point we may have to calculate that. But we see that we also are given the resistance of the line is 0.310 ohms per kilometer, and we're told how many kilometers away the city is. So it looks to me like the next step here would be, okay, how much total resistance is in the line 160 60 kilometers worth of that line? So if we take and simply do a little dimensional analysis calculation here, we've got a 0.310 ohms per kilometer. And if we multiply by the 160 kilometers cancels, and we get the total resistance of the line after that distance, which 0.310 times 160 would be 49.6 ohms. We can now go ahead and calculate the final power at the city. And we could do that by simply doing an I squared times an R. Again, you know, the current remains constant. Our resistance was 49.6. And so when we calculate that, we get a 4.96 times 10 to the 7th watts. Let's see if our answer makes sense. We started out with initial power at the power station of 7 times 10 to the 8th watts. We should end up with less power at the city because there's a potential drop after that distance. So we lose voltage, therefore we're going to have less power. And indeed, we have a final power of 4.96 times 10 to the 7th watts. So now we're able to go ahead and we can calculate our power loss, which was our initial 7 times 10 to the 8th watts minus our final 4.96 times 10 to the 7th watts. And our power loss, therefore, is 6.50 times 10 to the 8th watts of power. All right, so there's our answer to A. Let's move on to B. Refocus on what we're doing here. What fraction of the transmitted power does this loss represent? Well, as mentioned, the fraction would be the final over the initial. The final was our 4.96 times 10 to the 7th watts, and our initial was the 7 times 10 to the 8th watts. Our watts, of course, cancel, and expressed as a decimal, we get 0.071. Often what we like to do as physicists, okay, that's great, but let's express that as percent, and that would be 7.1%. So that is a 7.1% loss of the transmitted power from the power station to the city. And that's the end of problem 1.